22 states of matter you won't believe exist. Welcome to our deep dive into the fascinating world of matter. Today, we're exploring 22 different states of matter, some of which you might not have heard of before. You know, when we think about matter, we usually picture solids, liquids, and gases. But the universe is far more imaginative than that. Get ready to have your mind blown as we venture beyond the familiar and uncover the secrets of exotic states of matter. Let's start with the basics, solids. We encounter them every day. A rock, a chair, your phone, all solid. What defines a solid is its rigid structure. The atoms are tightly packed, vibrating in place, giving the solid a fixed shape and volume. Think of it like a well-organized party where everyone is politely keeping their distance, but still close enough to interact. But even solids can surprise us. Under extreme pressure or temperature, their structure can change, leading to fascinating properties like superconductivity. Now imagine that party getting a little wilder. People can move around more freely, flowing past each other. That's what happens in a liquid. The atoms are still close together, but they have enough energy to break free from their rigid positions and move around. This is why liquids can flow and take the shape of their container. Water, the elixir of life, is a prime example. But don't be fooled by their fluidity. Liquids can be incredibly powerful, carving canyons and shaping landscapes over time. Okay, now the party is really hopping. Everyone's moving at high speed, bouncing off the walls. That's your gas state. The atoms or molecules in a gas have so much energy that they overcome any attractive forces and spread out to fill whatever space they're in. Think about the air we breathe, a mixture of gases like nitrogen and oxygen, constantly in motion. From the air we breathe to the vast clouds of gas and dust in space, this state of matter is all around us. Chapter 4. Now crank up the energy even further. We're talking about temperatures so high that atoms start losing some of their electrons, becoming electrically charged ions. Congratulations, you've created plasma. This ionized gas is a hotbed of activity, with charged particles zipping around, creating electric and magnetic fields. Plasma might sound exotic, but it's the most common state of matter in the universe. Our sun? A giant ball of plasma. Those dazzling auroras, you guessed it, plasma interacting with Earth's magnetic field. Chapter 5. Hold on to your hats, because things are about to get seriously weird. Let's talk about excitons. Imagine an electron, usually bound to an atom, getting excited and jumping to a higher energy level, leaving behind a hole. This hole acts like a positively charged particle, and it can attract the excited electron. This bound state of an electron and a hole is called an exciton. Now pack a bunch of these excitons together and you get excitonium, a bizarre state of matter that behaves like a superfluid, flowing without any resistance. Imagine a dying star, its core collapsing under its own gravity. The pressure becomes so intense that electrons are forced to get as close together as physically possible. This extreme squeeze creates electron degenerate matter, a bizarre state found in the heart of white dwarf stars. In this state, electrons are still bound to atoms, but they can jump from one atom to another, creating a bizarre kind of metallic bond. This electron gas exerts an outward pressure that prevents the star from collapsing further. If you thought electron degeneracy was wild, buckle up for neutron degeneracy. In even more massive stars, the gravitational collapse is so intense that electrons are forced into protons, creating a sea of neutrons. This neutron degenerate matter is the densest known form of matter in the universe, found in the cores of neutron stars. To give you an idea of its density, a teaspoonful of neutron star matter would weigh billions of tons. Deep inside neutron stars, things might get even stranger, literally. Some scientists believe that under the extreme conditions at the core, neutrons themselves might break down, releasing their constituent particles, quarks. But not just any quarks, strange quarks. This strange matter is a theoretical soup of up, down, and strange quarks, and it's thought to be incredibly stable. So stable, in fact, that some scientists worry that if a strangelet, a tiny lump of strange matter, ever came into contact with ordinary matter, it could trigger a runaway reaction, converting everything it touched into more strange matter. Don't worry, though. This is just a theory. Light is made of photons, massless particles that zip around at, well, the speed of light. But what if we could make light act like it has mass? That's the idea behind photonic matter. Inside certain materials called quantum nonlinear media, photons can interact with each other so strongly that they behave as if they have mass, even forming photonic molecules. This mind-bending phenomenon has the potential to revolutionize fields like optical computing and communications. Chapter 10, Quantum Spin Hall State, a topological twist. The quantum world is full of surprises, and the quantum spin Hall state is no exception. Imagine electrons confined to a two-dimensional plane, their spin, an intrinsic form of angular momentum, coupled to their motion. In this state, electrons with opposite spins flow in opposite directions along the edges of the material, like cars on a highway. This unique property makes the quantum spin Hall state a promising candidate for building future electronic devices that are faster and more efficient. Bose-Einstein condensate, the coldest place in the universe. Imagine a group of atoms cooled down to almost absolute zero, the lowest possible temperature. At this extreme chill, the atoms start to behave collectively like one giant atom. This is a Bose-Einstein condensate, a state of matter where quantum effects become visible on a macroscopic scale. These ultra-cold clouds of atoms are incredibly sensitive to external fields and can be used to study fundamental physics and develop incredibly precise sensors. Fermionic condensate, a superfluid symphony. Fermions, unlike bosons, are like the introverts of the quantum world. They follow the Pauli exclusion principle, which means no two fermions can occupy the same quantum state. But what happens when you pair up fermions, forcing them to interact? You get a fermionic condensate, a superfluid state where pairs of fermions behave like bosons. This exotic state of matter is helping us understand high-temperature superconductivity and other complex quantum phenomena. Superconductivity, the holy grail of electrical engineering. Imagine a world where electricity flows with zero resistance, where power lines never lose energy, and levitating trains become a reality. That's the promise of superconductivity. In this state, certain materials, when cooled below a critical temperature, allow electrons to flow effortlessly without any loss of energy. Scientists are constantly searching for new materials that exhibit superconductivity at higher temperatures, bringing us closer to a future powered by this remarkable phenomenon. Superfluid, flowing without friction. Imagine a liquid that can flow uphill, escape from sealed containers, and even slow down light itself. That's a superfluid, a liquid that flows without any resistance. This bizarre behavior is a result of quantum mechanics at work. At extremely low temperatures, atoms in a superfluid can all occupy the same quantum state, behaving like a single coordinated entity. Liquid helium, when cooled to near absolute zero, exhibits superfluidity. Supersolid, a contradiction in terms, a solid that can flow like a liquid. It sounds like a paradox, but that's exactly what a supersolid is. This theoretical state of matter is both rigid, like a solid, and can flow without resistance, like a superfluid. While experimental evidence for supersolids is still debated, this mind-bending concept continues to intrigue physicists and challenge our understanding of matter. In a typical magnet, the spins of electrons align in an ordered pattern. But what happens when you introduce frustration into the system, preventing the spins from aligning? You get a quantum spin liquid, a disordered state where the spins constantly fluctuate and interact in complex ways. This exotic state of matter has potential applications in quantum computing and high-temperature superconductivity. Imagine a fabric woven from tiny closed loops that obey specific branching rules. This is the essence of a string-net liquid, a theoretical state of matter where the fundamental constituents are not particles but these interconnected loops. This bizarre concept has profound implications for our understanding of quantum phases of matter and their potential applications in topological quantum computing. Droplets are familiar sights in our everyday world, but in the quantum realm they take on a whole new meaning. A dropleton is a quasi-particle, a collective excitation that behaves like a particle that forms in semiconductors. These quantum droplets are held together by a delicate balance of forces and exhibit unique properties that could lead to new optoelectronic devices. Crystals are known for their repeating patterns in space. But what about a crystal that repeats in time? That's the mind-bending concept of a time crystal, a system that exhibits periodic motion in its ground state, even without any external driving force. This bizarre phenomenon challenges our understanding of time translation symmetry and has potential applications in quantum computing and timekeeping. Imagine an atom, but supersized. That's a Rydberg atom, an atom with one or more electrons excited to very high energy levels, making it thousands of times larger than a typical atom. Now place this giant atom in a sea of ultra-cold atoms and you get a Rydberg polaron, a quasi-particle formed by the interaction between the Rydberg atom and its surroundings. In the first few microseconds after the Big Bang, the universe was a hot, dense soup of quarks and gluons, the fundamental particles that make up protons and neutrons. This quark-gluon plasma is thought to be a perfect fluid, with virtually no viscosity. By smashing heavy ions together at incredible speeds, physicists have been able to recreate this primordial state of matter in the lab, providing valuable insights into the early universe. Rydberg matter is a strange and wonderful thing. It exists in a realm between the world of atoms and the world of light, blurring the lines between the two. Imagine a gas of atoms, but instead of being tightly bound, the outermost electron in each atom is incredibly far from the nucleus in a highly excited state. These excited atoms, called Rydberg atoms, interact strongly with each other, forming long-range bonds that create a unique state of matter. Rydberg matter is incredibly sensitive to external fields and has potential applications in quantum computing and sensing. Thanks for joining us on this journey through the 22 states of matter. From the familiar solids, liquids and gases, to the mind-bending realms of time crystals and quark-gluon plasma, the universe is brimming with bizarre and fascinating forms of matter. Stay curious and keep exploring the wonders of science. Who knows what other secrets the universe is waiting to reveal?